Hi everyone, my name is Dyah. Today I'd like to present a paper from W 2020 entitled Few Shot Learning for New User Recommendation in Location-Based Social Networks. So many social network applications like Yelp, Instagram, and Facebook provide their user location-based features like location sharing. And this service encouraging the user to share the location whenever they visit businesses like store or restaurants. This resulting tremendous amount of user check-in data, which opens the opportunity to learn the user preferences and help the businesses by recommending new potential customers to them. However, in recommending new potential customer to a business, it suffers from data sparsity issue because most of the user did not visit most of the businesses. So if we create adjacency matrix between the user and the business, the matrix will be sparse and this could lead to less accurate predictions. So to handle the data sparsity issue, previous works use ancillary information such as geographical influence, social correlations, and temporal patterns. But for the LBSNs, the main accessible information is the geographical coordinates like latitude and longitude. However, most of the previous works in LBSN still using a raw distance or distance-based matrix to measure the relationship between the user and the business. And this could lead to two main limitations. First is distance may not be an accurate indicator to distinguish transportation convenience for each user. So for example, in this figure, we have two users, and these two users are 5 miles away from business A. But by only considering their distance, we cannot tell who is more likely to visit business A. But if we know the transportation preferences for each user, for example, user 1 tends to drive and user 2 tends to walk, we can measure the transportation efforts to make more accurate predictions. Second is the neighborhood of each businesses are not well modeled when making the recommendations. So for example, in this figure, we have two business business A and B, and both business are reachable for user U. They provide same service, but have different neighborhood information. So without knowing their neighborhood information, we cannot tell which business is more preferable for user U. Okay, so in general, this work wants to leverage these two informations. First is the transportation convenience, and the second is the neighborhood information for each business to improve the performance of the recommendation in LBS. So other than leveraging geographical influence to address the data sparsity issue, the author also wants to find suitable way to fully utilize the check-in data to improve the recommendation in LBSN. So they adopt few-shot learning framework, which is designed for learning with limited data, as the framework to fully utilize the sparse training instance. So they apply a metric learning-based few-shot learning framework by optimizing two types of instances. So what is few-shot learning? So few-shot learning means that we are making classification or regression based on only a few number of data. So that's why in the few-shot learning, instead of using terms training data, we use terms support set or support instances in this case. So these support instances is the labeled instances and serve as the references. So these references is used to conduct reasoning for our query instances. So here, in this case, we have two different query, the positive query and the negative query. Positive query means that this user is truly visit this business. But the negative query means that this user did not check in this business or fake check-in. So what they did is first they calculate the similarity between each of the query and the references. And then they compare the similarity score between these two. And in the end, they expect that the similarity score for the positive query is higher than the negative query. In other words, they expect that the true new user is more similar to the references rather than the user who did not check in this business. Okay, so there are three contributions mentioned by the author. The first one is they decompose the geographical influence into two information. First is geographical convenience, second is the geographical dependency. And second, they apply meta learning to location-based recommendation task and formulate them as the problem metric learning-based social learning. And the third is they present an empirical evaluation of this approach against 13 recommendation methods on 2 real-world datasets. So this is the architecture of the future learning framework. On the left side, there's three different sets. Two of them are the positive and negative query. The other one is the references. So the positive query is the observed check-in regarding this business, while the negative is the fake check-in where this user did not check in this business. And the reference set is composed of k random observed check-in, where in this example, k is equal to 4. And then we have two different modules. The first is the embedding module. It used to learn the representation of references and queries. And the relation module used to compare the learned representation and optimize them. So in the beginning, we fed these three set into the layer F to learn the initial embeddings. And then by going through the F layer, we will get the initial positive query embeddings, initial negative query embeddings, and also the reference embedding. And then next we have attention layer. This attention layer used to learn the representative of the references. And we have a self-attention layer, which is another attention layer, to generate the relative embeddings for queries. So these relative embeddings learns to use the references to explain the behavior in the each of the query. So in the relation module, we match each of the query set to the reference representative by using the similarity equation. So after we get the similarity for each query, we compare the score between these two. And if the negative query is more similar to the reference representative, ranking loss will be generated, and the model will be optimized by minimizing this ranking loss. Okay, so let's go back to the layer F, where it learns the initial embeddings. So there are 4 features encoded by layer F. The first is the business features. So these features represent the service, quality, and other business related factors. And second is user features, which represent user preferences. And the third is the features that indicating geographical convenience of business B for user U. So like the geographical location of business B and also historical check-in location of user U. And the fourth is the features indicating geographical dependency of business B, like the neighborhood information of the business B. So this is how they construct the initial embedding. So for the user embedding and business embedding, it's quite straightforward. But to model the geo-convenience embedding, they use Gaussian mixture model. So this Gaussian mixture model text to input from the user and business. And from the user is the user historical check-in locations and also the business location. And the other one is geodependency. So to model this geodependency, they use a graph convolutional network that takes the business neighborhood information as the input. And then they will concat all these four features together and feed it into the fully connected layer to get the initial element. So next, I will talk in detail how they model geographical convenience. So to model geographical convenience, they applied Gaussian mixture model. So it's a function that comprised of m component Gaussian densities. So here is the equation. So the probability of L given phi equals to the summation of each component Gaussian densities times the mixture weight. So each of component density parameterized by three parameters. First is the mean location factor mu. Second is the covariant matrices sigma and the mixture weights p. And these parameters denoted as phi here. So for a particular customer, given a set of historical tau check-ins represented by tau location factor else, the GMM likelihood will be like this. The PL given phi equals the product of each PL tau given phi. So in general, GMM will assume that there are certain number of Gaussian distribution in the user historical check-in, and each of this distribution represent a cluster. And the goal here to construct the Gaussian mixture model for the customer, each customer, for example here, customer U, and get the probability of the LB, which is the location for business B, given phi, that gives the geographical convenience of the business B for user U. Next is I will talk about how they model the geographical dependency. So here, the geographical correlations among businesses are modeled with a graph. So each vertex here represents a business with an edge with weight that gives the geographical distance between the business and its neighbor. And this work uses graph convolutional network or GCN to extract and aggregate neighborhood information for each vertex. So in order to propagate the features representation to the next layer, or we can say forward pass, they perform this equation. So the feature representation at layer beta plus 1 equals to the feature representation at layer beta times the width as layer beta. And they also take into account the A hat, which is equals to A plus I. So this A is the adjacency matrix. It used to enable the model to learn the feature representation based on the node connectivity. And they also added the I, which is the identity matrix, to capture business-owned features during the feature propagation. And then they do normalization here using renormalization trick by performing symmetric inverse half norm of the D or the degree matrix to the A hat. So this normalization needed to prevent numerical instabilities for the model to converge. So they pass this all of this to a sigmoid function. to get the feature representation at layer beta plus 1. So here, for example, HI0 represent the initial features of business I. So by going through this, the GCN, the information of I's neighbor will be get propagated to HI beta. So this HI beta not only represent the information of business I, but also that of its nearby neighbors. Next is the how they get the final query embeddings. So the query embeddings to get the final query embeddings, this query need to pass through two different layers. So the first is the layer F, then the second is the self-attention layer. So we already talk about how this query pass through the layer F to get the initial query embeddings. And this and now we will talk about how they encode this representation with attention to the references to get the final query embeddings. So in this case, the self-attention layer takes two inputs. The first one is the initial query embeddings and the reference embeddings. And these two will convert it into three matrices through linear projections and fit them into attention layer. So this WQ, WK, and WV is the projection matrices. Q stands for the queries, K stands for the keys, and V stands for values. So the self-attention result, or the QR here, learns the embedding by comparing the closeness between the query on all of the references. So in this way, the QR will encode the user business behavior of the query explained by the references. And they also employ the residual shortcut connection to derive the final representation and denote it as the QCOM. So the QCOM equals to the QR plus the original Q. For the reference embedding, so the representative or R bar is calculated as the weight sum of the references Ri based on the weights alpha I, which is derived from this equation. So this alpha I, to get this alpha I, each reference of the Ri fed into one layer neural network, and the output of which, together with the context vector VC, used to generate the importance weight of AI for each reference Ri through softmax function. And this is how they calculate the similarity and the loss function. So the similarity defined as the dot product between the R bar and the QCOM. So if the negative query is more similar to the references, the hinge loss will be applied to gauge the ranking error, where this gamma is the margin. So to evaluate the performance of the proposed method, the experiments are conducted on two datasets. So the first is the Yelp dataset, and the second is the Foursquare dataset. The Yelp dataset has 6 large cities, while the Foursquare contains 2 large cities. And the statistic can be seen in this table. So for the baseline, they divide this baseline into 3 different groups. So the first group represent the conventional method without considering geographical influence. And the second group is the conventional method with geographical influence. And the third is the deep learning method with geographical influence. And the proposed method itself, denoted as Seattle because it utilizes self-attention and visual learning. This is the recommendation performance for each of the method. So the blue dashed line here is the first group. The red dashed line is the second group, and the yellow dashed line is the third group. So if we observe from this figure, we can see that Seattle, the dark red one, the far right bar, it achieves the best performance. And the reason could be that the Seattle can models both geographical convenience and dependency, which express the power of the geographical influence. And this Seattle also adopts the visual learning framework to fully utilize sparse training instances, which is appropriate design for new user recommendation in LBSN. So to investigate the effectiveness of geographical convenience and dependency modeling, they conduct geographical influence analysis. So they create another three versions of Seattle. So first is the Seattle without convenience feature. Second is Seattle without dependency feature. And the third is Seattle with distance-based geographical features. So we observe here that when geographical convenience and dependency removed from the original Seattle, the MAP performance drops correspondingly. So we can safely conclude that both geographical convenience and dependency can improve the recommendation performance, and the geographical convenience contributes more. And compare with Seattle with distance-based, because the original is convenience-based, we notice that the Seattle with convenience-based can outperform the Seattle with distance-based in all 8 cities. And this demonstrates that the advantage of the convenience-based geographical modeling, since it can coach the user actual transportation efforts more accurately. So the conclusion is first, this work studied the problem of recommending new users to businesses in LBSNs, and then they formulate the recommendation problem as a metric learning-based visual learning problem in order to fully utilize the sparse training instance. And then they compose the geographical influence into two important information, which is the geographical convenience and geographical dependency. And they also present the effectiveness of this approach against 13 recommendation methods in 2 real-world data sets. Thank you. That's all for my presentation.